So let's start. Okay, so we're starting. And just a reminder, what we're after is what's called functional anatomy. Namely, what we want is small cognitive modules or linguistic modules, and we want to put them in small anatomical modules. That's the goal. And the question is, one, how small can we get? And two, how to define both functional and anatomical modules. With respect to defining the linguistic modules, we're going to start this tomorrow. But today we're going to deal with what counts as an anatomical piece, if anything. And this is just a small tribute to the world of phrenology that existed, that still exists today, arguably, but existed from the early 19th century, where people had this idea that, what you should do is look for mental faculties at different locations in the brain. And since there was no neuroimaging or anything like that, the idea was to look at the skull and look at different aspects of the skull in order to localize cognitive functions. The goal of this project was a racist goal. It was to prove the white supremacy. That was the thing. And, since different races vary in skull structure, the idea was to show that, white skulls are the best, something like that. So this is like as short as we can get. So the idea was to parcellate the brain somehow. And here you can see it's parcellated by sulcal, something like sulcal structure. Again, Photoshop is very useful for such things. And here it's not parcellated by anything. And the question is how to do it right. And what we saw yesterday is three approaches, just a quick reminder of what we've seen. We've seen three approaches to neurolinguistic experimentation and interpretation of results thereof. And, you can call these weak, strong and strongest, or something like this. And again, taking John Rusky's warnings, caveats into account, it's true that there's no causal explanation of any sort here, some weak correlations perhaps, but still it's important to make a distinction between what I call weak here, namely you use some measured continuous variables that you measure. It can be brain activity, it can be behavior of one sort or another, in order to pit linguistic hypotheses against one another. This is the stuff that you do in your daily toil. And the second one wants to do that, plus get some kind of idea of anatomical location. And the third one goes even further and tries to look for some physiological underpinnings. How explanatory is this? It remains to be seen. Let's see, what the market has to offer. We're not going to discuss that much of that from now on, but this is at least what you've seen is at least a beginning of that. Okay, we've seen three such things, and the fourth approach that's like all-encompassing, but it's not clear that it has much relevance to us. I will come back to this Goldstein paper and other related papers later on. I think the one thing to note at this point, at least, is that this work, with whatever deficiencies and advantages that it has, gets published in the top neuroscience journals. And one thing you might want to take a look at, and I suggest you go and read these things. I think we're going to put at least some of these readings in wherever Keely will be kind enough to avail us of. And I think you should take a look at it. It's a good idea. And one thing you might want to take a look at, just as a sociological observation about these things, is one, how many times each of these papers is cited. You can only dream about it, and you're at a good night. Like this paper, for instance, the Goldstein paper, last I checked was cited, it's from 2022. It was cited like 250 times. Okay, this is like well accepted stuff. And another thing you might want to take a look at is who reviewed these papers. Now, in many of the journals, you cannot see it. But here's one paper that you can see it in, which is Proceedings of the National Academy of Science, PNAS. They're obliged to do that. And if you're a member of the Academy, you get to select your reviewers 4 times a year or something like that. And one thing you might take a look when you find such papers published in PNAS, and there's quite a lot of these, in fact, from where's across the street, from across the street, you will, I think it's important to see who reviewed it. Okay, and the most important punchline is that typically linguists do not review these papers. Okay, so this is all I can say as of now. And when we look at anatomy, one thing that we saw is that the symmetry between the two hemispheres is not perfect. It's less perfect than you would like it to be. This is one thing that we have seen. And the history of anatomy is very rich and interesting and colored with all kinds of anecdotes and stories, but essentially the founder of modern anatomy, is Dutch anatomist Vesalius, who already at the age of 16 was waiting to the end of executions and was stealing bodies from the execution sites in order to dissect them. And one thing that you can see, and this was also something that was eternalized, but at least two paintings of Rembrandt. The anatomy lesson of Dr. Diamond is one of them. I think the more famous one is the anatomy lesson of Dr. Tulp. There are two such things. You go to Amsterdam to the Rembrandt Museum, you see them there, I think. And one thing that you can see is that even paintings of the time do acknowledge the lack of symmetry between the hemispheres, at least that. So this is one thing that shows you that the brain is not so simple, at least anatomical landmarks, namely topography, may not be the most important thing. So this is something that we discussed, and we said something about the topographic boundaries are not so useful. And I noted that about 2/3 of cortex lies inside sulci. In this kind of slice, you can actually see it. So what you will see from the surface hides everything that you see here and so on. And people have actually done these kinds of measurements to point out that a lot of cortical tissue, and this is cortical tissue, namely gray matter, white matter, we'll get to that in a second, a lot of it is buried. So relying just on those like hills and valleys is kind of missing the point. That's actually one reason why you see in many imaging papers, you see the brain inflated. So you can actually, it's kind of deformed, it's inflated in order to expose, or at least to model what you should see once the inner parts of the sulci are exposed. And the thing is, in fact, there's a world out there of modeling cortical folding. I learned it a few years ago. So there's a bunch of physicists who try to simulate it by building models of the brain from all kinds of materials. I think these are mostly material physicists, and they characterize each layer of the brain, and then they start folding it, and the goal is to get to the way brains are folded, and then they actually do these kinds of things. You can see different stages of folding, supposedly different embryonic stages, and it has an independent interest, but the important thing is it's not clear that there's any systematic relationship between this folding pattern to what we see. So it's not at all clear that the brain topography is a good system of landmarks for us to have anything to do with function. But luckily there are some and when you look across brains, so this is work that came out of some colleagues of mine at McGill, a guy named Michael Petridis in his lab a long time ago. And what they did was they characterized the posterior half of Broca's region, something called Brodmann 44, we'll come back to that. They characterized it by the sulci that encompass it. And they just went by this definition to 50 brains. They took 50 McGill students, they scanned them, they built a 3D model of that, and then they had somebody sit with somebody who knows anatomy, sit on all these 50 different brains and mark by these topographic instructions, mark the area that is encompassed by the topographic instructions, which is supposed to be the topographic perspective of the posterior part of Broca's region. That was the idea. And I'm showing you 10 of them, and you can see the good news is that everybody has it. The bad news is that they don't look alike. So there's a lot of variability here. But luckily, there are other perspectives on functional anatomy. One perspective is histological, namely looking at brain tissue microscopically. Another one denies it altogether. It's what's called like just functional anatomy. This is actually what's practiced most forcefully, I think, across the street. Now that I know that it's here, the person who pretty much started it was Nancy Canwisher, who started doing functional anatomy in a particular way about 20 years ago, over 20 years ago, actually, in face recognition. And then this method got carried over to language by Fedorenko and other people, and we can discuss that. But the important thing is there are alternatives to topographic anatomy.
And what can you like just with like of course like people like us who don't know anything, we look at this and these look like, well, somebody tells us these are the same. These are like, this is where this is located in the different ranges.
As I said, there's a definition, and it says Broca's region is, or area 44 is that little hill or gyrus that is surrounded. It's like a definition of borders, of country borders. Okay, so one example I always give about the barrier of Salsai is the border between Canada and the United States. Okay, so there's a place called 1,000 Islands in Ontario, which I think is like, it's close to upstate New York. And in the midst of it, there's 1,000 islands. You should go take a boat tour. It's actually very nice. Okay, and there was a debate of where the border is within the St. Lawrence River. So the St. Lawrence separates the United States from Canada, but it becomes relevant, either that there are like issues of fishing rights, which is not the case there, or when there's 1,000 islands there. So there's actually an island that's about, I don't know, 50 feet long or something like this, and half of it belongs to the United States and half of Canada. This is just an arbitrary agreement between politicians, and you don't want this to depend on arbitrary agreements. That's my only point. So how similar these are, well, it depends. But it's not as if, when I start teaching this, I usually say, we all think that when we talk about a point in the brain, we know what we're talking about, because the brain is just the brain. But wait a second, look at everyone's noses. There's a huge variability in nose structure. Why should there not be variability in brains? And it turns out that there's a lot of variability, and this is a big problem.
But you're saying nevertheless, there's still a meaningful identification of
You mean topographically?
Yeah.
Kind of. We'll see the lack of, in a few slides, you will see that, there is another aspect of anatomy, the microscopic one, and its correspondence to the topography is not great. So kind of. Okay, so now, this is just like a straight up slice, and you see, there's this folded stuff. Everybody knows there's white matter and gray matter. You have to stain these things. It doesn't come for free. You don't see it. It doesn't look like this when you just slice something. You have to stain it in a manner that accentuates certain kinds of things. Details aside, you see here, there's a fairly clear thing that is called the cortical ribbon, which is what you see here, the gray matter. And the rest of it is a lot of connectivity, which of course is extremely important, but this is not our focus right now. It's important to know that it's extremely important, but that's not what we're focusing on. We're just focusing on cortex. And when you look at it in the microscope, you actually start noticing that there's some kind of laminar structure inside here. I'm gonna show it to you in a much bigger way. And here you can see somebody, and this somebody was actually Brodmann. This is taken from his original book in 1909, and he actually marked different layers in cortex. And this is an important concept, the laminar structure of cortex, and we're going to start seeing what it is. So the idea behind it is that when you start looking, and this is just a schema, when you start looking, you see that there are different kinds of cells and different kinds of what's called cell packing density in each of these layers. And if you're a serious anatomist, as these guys were in the, starting from about the 1870s or something like this, they spent their lives looking into microscopes, and they had these huge drawing blocks, and they would just sit and draw all day. And these things are actually, they exist. In Düsseldorf, there's an institute with a lot of this stuff. It's very impressive. So there is some in a structure that may have functional relevance, because if you have a typology of cells by their morphology, and if you believe that this morphology has functional relevance, and there are independent reasons to believe so, like I think probably half the class has heard about pyramidal cells, the pyramidal system, and the connection to the sympathetic and parasympathetic system. It's like high school biology. At least it used to be. So there seems to be some functional relevance to this morphological typology, which is made just by observation on dead tissue. Of course, this is taken maybe not from humans, but from something. And if you start looking a little bit, you magnify it just a little more, you start noticing that there's some kind of there's a sense of a flow here. I think it's difficult to deny that there is a sense of a flow. And somebody, which is also, once again, it's Brodmann, marked those layers for us. And the question is, can this be done seriously? So 19th century and early, actually up to the mid 20th century, anatomists would sit there, spend all day, establish criteria for what counts as a layer, and then try to use these criteria across the brain in the same manner. And it's difficult. It's subjective, on Monday morning, you don't do it as well as, or you do it maybe better than you do it on Friday afternoon. I don't know, depending on your views of the weekend or something like that. It's really difficult. And the question is, can you actually do it? So is this really a valid generalization? This is actually the question. Is this schema really valid? Does it hold when you start checking it? And the answer is, yeah, kind of. Biology is always kind of, in many respects. So people have actually done it. And here's the most important observations by a guy called Corbinian Brodmann, the same person who gave his name to this Brodmann areas. Okay. Some of you may have seen this little schema, which represents very little, unfortunately. But his point, what he got famous for, are several observations. First of all, throughout cortex, you see these layers. Secondly, the important thing is, and you might ask yourself when you look back here, if you look here, actually here, I'm sorry, I misordered the slide. The important thing is when you start moving from this part to this part, the question, I'll take it back a second. If you look here at the pattern that you see, and I realize it's not big enough, and you look at this edge at the pattern that you see, they're obviously different. Here it's more scattered, here it's less scattered, here their gaps are quite clear, here the gaps are not as clear. This is like very superficial criteria. And the question is, what happens when you start moving your criteria from here to here? There will be change at one point. Will it be abrupt or gradual? If it's going to be gradual, there's very little we can do with it. The remarkable thing is that the change is actually abrupt. And this is the biggest, I think, discovery in neuroanatomy of the 19th century, that the changes are abrupt. And that actually brought people, not necessarily Brodmann, but he had articulated it very clearly, to call those abrupt changes border, because they, in the sense that they enclose areas microscopically. And the idea is, and the hope, okay, is that this cytoarchitecture, the architecture at the cellular level, okay, this cytoarchitecture reflects some pattern of functional connectivity at a local, in a local way. And the idea is that this functional connectivity supports a specific function. So the notion is why would two areas that are adjacent be different? Well, they are different because they support different functions. Maybe why is not exactly the question, but what's the difference between two anatomically distinct, micro-anatomically distinct areas? Well, they support different functions, so their internal organization and makeup is different. That's the logic behind it. So this is like the leading hypothesis that leads this whole endeavor. It's not as if people are just looking for documenting phenomena. People are looking for documented phenomena in a way that's hypothesis driven. And the hypothesis here is, as I, basically echoed it early on, small functions in small brain areas. What characterizes brain areas? This group's answer, and I happen to align with them, what characterizes them are microanatomical borders. What are the functions? Let's find out. Okay, yes.
Do people ask whether, speaking sloppily, the border could be an aspect in which you have a particular function?
You mean the border itself?
Yeah, exactly, right? So you could actually, I could imagine that you could define functions where the border is like a switch between two things that do something, but it's the switch that's the function.
Let me tell you how these borders are discovered to begin with, and then we can discuss it. I mean, life is not so great, but let's see, okay? So yeah, so what's important, and this is the problem with Brodmann's approach, and you can see it in the two critiques. First of all, what I, much to my shame, I learned about this only about 20 years ago, which in my life is not such a big fracture anymore. That Brodmann's work was based on the analysis of a single human hemisphere. Probably, it's not even clear, okay? The reason for it, I used to say, since I'm a well-known Germanophile, I work in Germany and been doing this for many, many years. It's only, I can say it with like open heart, it's only in Germany that people could have done this because they don't look for immediate credits. They want to discover something. So it's still true to a large extent, I think. Many German scientists are happy to work without publishing for a decade, and they work really, really hard. This is extremely unrewarding work. It's a lot of work. And what Brodmann did is he wanted to have some kind of evolutionary scale of brains. So he started, I think, with a rat, or maybe with a mouse, I'm not even sure. And he wanted to build up some kind of an evolutionary scale. And of course, he got to the human brain late in life. And he only analyzed one hemisphere, maybe two, but one at least, and two at most. Okay, something like that. And because of that, there was no concept of individual variation. Now, I started out by emphasizing individual variation, so let's see what you do with it. I'm not even talking about the fact that it was observer dependent. So we have to get a little better. And to underscore this, and you have to realize everything I show you is based on work by Katrin Amunds and her colleagues. This is in Jülich, Germany, Forschungszentrum Jülich. Okay, Katrin Amunds is the leader there. She and her mentor at the time, who since passed away, Karl Zillis, developed this approach, and you're going to see it. And everything is not stolen, because I took it from my friends. Can you
I always say that.
What?
I said I always say that.
You always say that. Okay, I'll say just like Danny. I will say that too. So the initial paper of theirs looked for 10 different brains, did the mapping by Brodmann's criteria, except did it mechanically, computationally, about 25 years ago. This, I think, is from 99. And one thing they pointed out is that even without analyzing many brains, just looking back at the literature, you notice that different anatomical groups in the 20th century, these are three different brains from three different groups, the best anatomists of the first half of the 20th century, and you can see that the brains are very different. First of all, they look different. One is big, one is a little smaller, one is more spherical in structure, the other one is kind of flat. And then they marked what had been the two pieces of Brodmann's areas for these three anatomists. Now you have to remember, these people, it's not because they didn't know how to draw. These are extreme. I've never seen people who are more visual than anatomists. They know, and they know how to draw. This is what they saw. And everything is supposedly compacted into this ridiculous kind of image that everybody has in mind. They don't look, and these are the two areas. So they don't look the same. So let's see what you do. Here, this is the picture. So this is Katrin, this is Carl, passed away, a dear friend of mine. And you can look at the two areas and judge for yourselves that they actually look different in terms of the laminar structure. Now, when you think about this laminar structure, what exactly does it mean? Well, what it means is that if you take if you draw a line that, let's say, is perpendicular to the tangent here, you just draw a straight line from the surface of the brain, which is this fatty tissue here at the top, to the white matter, which is somewhere here. If you draw a line and you want to characterize a profile of this line, but let's say by degree of grayness, you will be able to find some kind of a pattern. And then if you draw another line that's next to it, it would exhibit pretty much the same pattern. But if you draw a line here, it would exhibit a very different pattern. So, I even have, so here's, you draw a line, and then you draw another line, and then you draw another line, and another line. And what they did was they found a way to characterize a profile by something that they built. It's called gray level index, which, you know, when you digitize something, you can get your impressions of the visual stuff. You can convert them into a number. And they found a way to characterize a profile. And then they started, in order to establish a border, they started with a moving window. I think this is where it comes. It's a moving window, okay? And the question is, when you move your window with several such slices or profiles thereof, when will you detect an abrupt change? And once you have a profile, you can build some kind of statistical characterization of what counts as similar and what counts as different. And let me show you how this works. So they had a bunch of brains, and these brains gets sliced. They first get fixated because the brain is soft tissue, then they get sliced. And just to show you how complicated it is, you should see how she does it. It's shocking. You know, she gets this extremely distorted sheet. It's 20 micrometers thick, and it's extremely distorted. And then you have to correct the distortions and all kinds of technical issues. And you get these slices, and then you digitize them. I mean, first you digitize them. You use these just for verification. There's a high-res camera that's looking at it at the top and converts it into a digital image. Okay, there's about 7,000 slices per brain in a way that's quite permissive, actually. It's like, I think, 5 millimeters between every two slices or something like this. And this is what you see. So when you look at it, you start seeing, you know, you look at it, or it's digitized reflection, you start seeing that actually the patterns in terms of degrees of grayness vary. And you can characterize them by this. This is exactly what I had in mind before. If you look at a particular point and you go from, let's say, the outside into the white matter part, you can characterize it by some kind of a pattern in terms of degrees of grayness, so whatever index that you build for this degree of grayness. And the question that you might ask yourself is, when will it change? Okay, and when will it change? That's the idea. And here you can see this is something this is exactly what I explained to you before. This is exactly what you do. And then you look at two different places and you ask yourself, by some kind of multivariate measure, which is called d squared or Mahalanobis distance, you ask yourself, when would the measure of similarity exceed, or the measure of this similarity exceeds some threshold, and this is what you call a border. This is the idea. So it's not as sharp as you, I mean, it's sharp if you use the right statistical binoculars, but that's as far as it goes. So it's not as if you can point to it like that. And this is work that you do on every slice, in every brain area, on many brains. You need to do this. So if you do it on individual brains, yeah, I don't know why this is like a summary. Okay, so here you can see the two different areas. You can see that the patterns of the grayscale index differ from the yellow one, which is 45. This is right, happens to the right hemisphere, and the reddish one, which is area 44. And then the point at which, you know, it stops being the same is deemed to be the border. One thing that I asked, and I have to admit I never got a clear answer, is do you get the same border when you go left to right or right to left? It's a non-trivial question. So the question here is, if you move your window whose size is arbitrary, okay, if you move it from this part into this part, does it mark exactly the same border than if you move from here with your moving window coming from here and you move it in the other direction? I never got a clear answer. Okay, these are complicated issues. It's not that people are vague. So this is one thing that you see, and the end of it is you establish a border. So again, it's biology, it's give and take a bit, but it doesn't diminish the force of the distinction. Yeah, you can see there are all kinds of other traits if you're a serious anatomist that you can identify here, but not there, and so on and so forth. And you end up building 3D models, and you can see this is the two primary and secondary visual cortices, and you can see them in 10 different individuals, and you can see that they're pretty similar. This is site architecture. It's like superimposing on the 3D model of the brain, superimposing the individual brain, superimposing this particular perspective, namely cytoarchitecture. And the primary and the secondary visual cortices appear in everyone. They're roughly symmetric between left and right, again, very roughly. But and the variability is actually not that great. So this corresponds to these two areas. And when it comes to Broca's region, we can see what it looks like. These are three different brains on the 3D reconstruction of the histological, the microscopic stuff, reconstructed onto 3D. And you can see again, there's variability, but for these three subjects, they do exist. And the question now becomes, okay, now that we have parcellated it thus, what do we do with groups of subjects? And this is why I was kind of hedging when I didn't answer Martin's question, because even if we assume that we can actually make this division clearly for each individual, and turns out that we can, the question is, what do we do when we lump a bunch of subjects together, given this kind of variability? Now, for many people, the solution is, let's just forget about anatomy, it's complicated, let's just forget about it. I think most people in cognitive neuroscience, let's just forget about it. But wait a minute, maybe it's the truth. You know, I don't know of any preferred perspective on you know, the ultimate truth.
This is like,
Just be louder, I'm deaf.
yeah, I'm loud, yeah.
You're loud, but I'm deaf.
So like a lot of the surface variability, you would imagine that, you know, if you ask the right geometric questions, you're going to find identity across all brains. For example, if you ask adjacency, like presumably in every brain, the yellow part and the red part are adjacent to each other. So that, you know, you don't find the yellow part here and the red part here. Aside from the fact that they look very different, but there are certain structural relations that are going to be fixed across all brains, one would hope, right? wouldn't that sort of question be the one, like, the fact that you look at things and, every particular thing looks different from another particular thing as such, I'm not sure if it's, like, everything looks different from everything else, it's a little bit unclear what to learn from.
No, but your
wouldn't the
criteria-
point have to be to
But
abstract
your,
away?
but your criteria for what constitutes an area and how to discover it remain constant across brains. It's not as if you change the rules when you move to the next brain. And still, you can say it's a big surprise, but it should actually confirm your hunch that this is something real. You go to the next brain using the same criteria. And in this case, the criteria are formalized by some kind of a computational model that you impose on it. And you do discover this area in the same location, except it doesn't look exactly the same. It look and how, what does it mean to be exactly the same? We don't know. We have to discover it. Okay, I'm kind of non-committal in my answer to you because I think the right approach here is to stick to the biology. And the important thing is to keep remembering that the criteria for the establishment of these are biologically driven. That's the best answer I can provide. And so, perhaps from a geometrical point of view, you can find all kinds of similarities between anything and anything. In fact, Catherine has a nice way of saying it. She says, you should always remember that you can take you can take a brain and turn it into a Volkswagen. And I think for me, it's a fantastic way to think about, like all kinds of transformations from one brain to the next.
Yeah, right. But, imagine like a hypothetical situation where there are a certain number of brain areas, and each brain area is anatomically identified on the basis of its adjacent areas.
On the basis?
Of what areas are adjacent to it, attached, connected to it.
Right.
Like in a literal sense
Right.
that there is nothing else in between. As such, this already gives us like some kind of a map, right? It doesn't matter what they look like, it doesn't matter how big they are. We already have like a way of basically, if you know what is next to what, as long as you can orient yourself whenever you see the brain, you will always be able to somehow identify.
But so tell me, is there a way for us to know how many such areas there are?
No, that's a methodological question, but like
No,
that's
it's not
a discovery
this is an
question. Like,
empirical
that's what
question.
No, but that's what we like to understand. But the point would be that under that sort of a view, which we don't know if it's true, and we don't know how many areas there are, and I imagine we don't have the map, I guess, whatever. Whether or not these things look similar to each other is irrelevant, and the only thing that's relevant is what's next to what. Right?
We don't know that.
No, we don't know that, but shouldn't that sort of question be the sort of question that we should try?
It's a good question, but it's a question. That's my only point. And it's not as if, you're fishing in the dark. And I guess the most important lesson, which you would be, I don't need to convince you of it, of course, which is don't take anything for granted. And here, like you would be the last person that needs this kind of pontification. But the thing is, nothing is given in advance. And when you discover that everyone has it, forget about, let me echo what you said. You discover that everyone has it, forget about its exact shape. It's less important. Yes, but it turns out to be more important once you want to use it as a localizing tool. And that's the goal here. So I do agree with you that if all you said is, I just want to know how many areas there are, and I want to know where roughly they are, and because each of them is defined by its neighbors, then I don't really care if it has like a little edge here and a little corner there. I don't really care. Okay, it's fine. And it's easy to agree with you that this is one way of looking at it. But now, what is it good for? Okay, here's what it's good for me, and I will get there in just 2 minutes. It's good for in order to use it as some kind of a localizer. It gives me the notion that there is an anatomical piece in which a particular function I'm interested in lives. Okay, so in order to establish that it lives there, I need to know where it is. And if I want to test more than one way of doing it, it's just restricting myself to a single brain, which in fact was the approach of the most important to date, the most important brain mapping reference, which is something called Talirach and Tournou. Okay, they used a single. There are two French neurosurgeons who used a single brain in the late 1980s. It turned out that this brain belonged to, I think, a female who had who later on turned out to have had major psychiatric problems, which may have affected her brain. And what they did was they looked at this individual brain and said, let's just not care too much. We just want some kind of a coordinate, like a reference space for other brains. And then they use, this is their work. They use this, it's like a fishnet to superimpose on their model. And they said, okay, so now we can actually say that something is in area 44. So they took it from Brodmann, they made the graphic a little nicer, and they superimposed it on that single brain. And this has served since, for many people who don't know enough about anatomy, it has served as a way to say, I'm in area 44. And you can see immediately, given the variability that the Yiddish work points to, you can see that it's ridiculous. So this is the problem. So in principle, if all you need is just to establish a map, if all you need is just to know that there's an area, then you're right. But this is step number one. Step number two is to make use of it. Okay. So now we're back to Danny's question, which is the relationship between topography and the other kind of stuff. And here, they didn't color coordinate exactly these two different papers, but roughly, and it's not the same subjects, but roughly, everybody has it, but that's about it. Yes.
I got a little confused by your response to Amir. So, can you explain what exactly is the criterion for determining what is Broca's region, or what is
So first of all, again, the criteria keep changing, but the criteria are always have to do with the two aspects of it. One is, as Amir pointed out, I think in the most succinct way, Broca's area is that area that is bounded by X, Y, and Z. That's one way of looking at it. But more importantly is Broca's area is what the anatomist tells you that Broca's area is. Namely, the anatomist would have a method of going into this particular gyrus and then seeking within that particular gyrus, it's called the angular gyrus, and seeking within that angle, these things have names and it gives you an impression that it's the ground truth, okay? And because they've had these names for 150 years, maybe more. Okay, so you go to this particular, actually this is not the angular gyrus, I'm wrong, but never mind. Then you go there and then you can parcellate it into the two different pieces. But if you look inside, you find this kind of cell and not that kind of cell. Okay, so you start off from biological definition, and it's to me always interesting to see the dialogue between the computationalist and the anatomist, because it's always a give and take. It's the way you guys work with primary linguistic data. That's what you do. It just happens to be in the same person, but you write a paper. You start juggling between your theoretical approach and your data. It's exactly the same thing here.
So the second kind of method means that Broca's area and different people resemble each other with respect to grayness patterns or something like that?
Yes, okay. And I will show you so here I'm showing you the visual cortex in 10 different individuals. And when you look at that, you see that everybody has it and it's kind of symmetrical and it's the same in the same location in let's say brains, like a 3D, some kind of a division. I'm not going to give you lectures about reference spaces. This is really not the point here. So roughly it's the same. And again, in biology, there's a lot of roughly, which doesn't make it less precise, but up to biological resolution.
clarification question on this. I thought earlier you said that the Jülich method, retracing Brodmann, was to ask the question of, can I detect a phase transition or boundary, right? That isn't the same within a region, right? If I'm giving you this chunk of cortex, and now I'm running my algorithm of slicing and moving window and determine a computationally implemented criterion when there is something changes abruptly. That gives you a boundary, and we can ask what are the boundaries that I can get within a stretch of cortex, right? But what Henri said, or what you said to Henri's question was, we agreed to it. Henri said it's the cell structure itself that says that's Broca's area, and I can look at it. That's different. Because you could imagine that you have the same boundary, but internally you have very different
Yes,
cytoarchitecture.
But let's go back to the first part of your question, of your comment, okay? And the first part was, you set up an algorithm, and the question is, does this algorithm identify it properly? Let's just ask, how did you set up your algorithm? And my point is, you set up your algorithm, they did, by a very complex dialogue between the computationalist and the anatomist. This is the way it worked, you know, and this is the way it works until today. You know, they set up a bunch of criteria. I remember the first time I spoke to their algorithm writer, a guy named Axel Schleicher, and I talked to him a little bit, and he said, "Look, I know about layers. I'm an expert on layers, so he knows how to do layers." And he comes from the world of computation, and Carl Zilles and Katrin came from the world of anatomy, and they started the dialogue. This is how it worked. So the input from biology was critical. Without input from biology, there's nothing that you can do. And the important thing here is to remember that this is biology. The computational tools are just tools. It's like getting an average.
But so one sharp point here of interest is, I think, whether we want to commit to each border giving us on its left and its right, or whatever, multiplied by n, identifiable different cytoarchitecture in that level or not, or whether you could have exactly the same, you know, combination of various neuron cells, various types of cells over here, as well as in visual cortex. But what you do observe first.
These are great points. These are great points. Okay, and again, I can't elaborate too much on it, but what they tried to do later, first of all, they set up the division, and then they wanted to get in the. You know what? Let me progress for 2 minutes, and then I'll get back to it, because in fact, my last slide talks about like independent evidence for this, and then I will go back to your question of whether you can characterize each area independent in its own right as some biological entity. Okay, I'll get to that. These are great questions, you know, but until last year, Katrin had a team of 120 scientists, and it's not enough. You have no idea how much work and how much sophistication this kind of thing requires. Okay, it's just hard work. Okay, so fine, this is just, here we see, we're back to Danny's question earlier on, namely the relationship between topography and the cytoarchitecture. So you get like here, you get like 3 brains, I think. Yeah, I just cut it. It's the same paper, this landmark paper about Broca's area that in fact brought Katrin and me together. She's my longest collaborator. It's almost 25 years now. And one thing that you can see is you take the brains on which these areas were identified microscopically and algorithmically, and you superimpose them on the very brain from which they're taken. And you notice that, first of all, within different individuals, so each of these pair of hemispheres is a different individual. And you notice that for each individual, the size, the location, and the exact position varies. Again, it brings us back to Amir's point, of course, which is why bother? let's just suffice, or let's be content with the existence of such an area in each individual. And in a second, we will see that actually a way to get some traction from the group. But you can see that the correspondence is not fantastic. And this is not even microscopic, you know, you can see these are big brain pieces. It's not great. That's life, you know? Okay, so the question is there a correct unit for functional analysis? Because, you know, in case you forgot, we're talking about a function that's called language or linguistic knowledge. Okay, so this is the end product. And what you can see here, the solution, as it were, is what's called probabilistic maps. So here is what you see when you superimpose 10 brains. You know, you normalize them somehow. There's a lot of normalization and again, turning a brain into a Volkswagen on the way and things like that. But when you take 10 different brains and you pass them through this fantastic process, and then you superimpose them on a single template, and you ask yourself, what's the degree of overlap? Or in each voxel or pixel in this slice, let's say, in each pixel, how many brains mark this particular one for area 44? And you can see on a scale from 1 to 10, the picture isn't fantastic. There are tons and tons of issues, but you end up with these kinds of probabilistic maps. This is the same kind of thing, except more elegant, because, you know, it's more graphical and it's done by a supercomputer and things like that. And essentially, the hope is that you end up with something that looks like this. The whole brain is divided. There are tons and tons of issues here, namely, with respect to Martin's question about the boundaries, you can see that the boundaries here are very sharp. And the boundaries here are not sharp at all. There is no boundary, in fact. And the question is, how do you decide on the border between Broca's area 44 and Broca's area 45, the other way around, given that this is so dull and there's overlaps? I can answer you later, not right now, but you can see it's problematic. And this is some kind of a visual thing. Many problems, many issues, but here's the use of. So this is like for Amir to answer the question of what is this thing good for? And here is how it's been good to me. Okay, you take this map, which is the red stuff here, you get some kind of a functional image of some function. In this case, it's roughly movement, syntactic movement. So this little yellowish dot there is the maximum or close to the maximum and its surroundings of what gets activated when you manage to distill syntactic movement out of all the noise in the world. And now you take the functional map that you obtained and you superimpose it on the anatomical. And this is what you get, bingo. Okay, a similar thing has to do, and this I will start discussing tomorrow, with, let's say, monotonicity. Okay, so one thing that you can see here, if you look at this, you can see these two brain areas, namely 44 and 45. I will stop it, let's say here. Did I stop it? Yes. Okay, so these are the two language areas that we just discussed, the yellow and red. These are the two language areas, and what you see here, I will show it to you in larger ones, is what gets activated by something like monotonicity. And we'll discuss it in more detail, but something of that nature. And now you ask yourself, how does it relate to the language areas? And the answer is, one, it excludes the language areas. It's not there. Two, is the blob that's identified by whatever manipulation you did in your experiment, in the functional MRI experiment, given that it excludes the language areas, is it contained within an anatomically coherent area? Or is it just some kind of an accidental finding because there's so much noise in this world? Answer, let's go and see whether we can identify within this area. This is in this thing called insula, which I said is a piece of cortex that's kind of isolated. The insula is very big. It consists of many cytoarchitectonic areas. And the question is, can we see coherence in terms of the anatomy of this area that's identified? It's a serious question. And the answer is yes. This is like maybe one of the first cases ever where the function led to the anatomical question, because I told them, go and find it for me. I'll show it in more detail tomorrow. And it turns out that it's anatomically coherent. This is a new piece of information that I just taught you, okay? And I was able of informing you of that because of this probabilistic atlas that said it's the same for everyone, module of some variability, and it does capture a functional distinction in a good way. So this is an example of like very small linguistic function, and let's postpone the details to tomorrow and next week in the seminar that I'll give here, and the small anatomical piece. So it is, if you want, some aspect of the modularity of some cognitive function. So this is the use of it. Here is one last use, and I will stop in just 1 minute. You can also use it in order to calculate the amount of area that is destroyed by a lesion. So here, instead of superimposing on the anatomical atlas, instead of superimposing the function, we impose the lesion map. And we can actually see how much area of each area is destroyed for each of these, and hopefully try to correlate it with function. I can already tell you the results are not great, okay? But still, that's the only tool that we know. Last point, which relates, okay, let's forget about this. Last point that relates to one of Martin's questions. You want independent evidence to believe that these borders are any good for anything. So here's what they did. It's the same group, Carl Zilles, Nicola Palomero Gallagher, and some other people. And what they did was they said, look, one important aspect of, 1 minute, Ananda. Okay, one important aspect of functional anatomy is receptor distribution. So they found a way to neurotransmitter receptors. So they showed that, in fact, if you map out the distribution of receptors for specific neurotransmitters, and you map it in the same way, the concentration of receptors, or the relative concentration of receptors, respects the cytoarchitectonic map. So this is an aspect that's clearly functional, in which you can see that the anatomy has small parts. And finally, and that's your question, and I will stop, they then took this and tried to characterize each area by its own profiles, okay? They call it like a receptor signature or something like this. And the results are not bad, that you can actually distinguish between two areas and find similarities and so on. Tomorrow we'll continue with monotonicity. Bye. Thank you.